So you've been told that BeSang's True 3D IC is an ultimate solution for producing more die per wafer while still maintaining roughly the same manufacturing costs as conventional 2D ICs. But how does it work? Well, conventional integrated circuits such as memory devices and CPUs are two-dimensional, with the memory core and logic lying side by side. BeSang's True 3D ICs are vertically stacked, with the memory cells stacked on top of the logic devices, thus reducing the chip size by 50 to 80% depending on the product. This results in 2 to 5 times or more die per wafer, and therefore higher productivity. Given the broad overview, some questions you still have might be, well, aren't there additional process steps for 3D stacked devices? What about the material costs for thin semiconductor layer formation in 3D stacked devices? And adding layers vertically generally degrades yield. What is BeSang's solution for this yield issue? Let me elaborate more on these issues. One common misconception regarding BeSang's 3D IC is, well, wouldn't this entail more steps in the manufacturing process? The answer can be yes or no, depending on the application. However, generally, the answer is no. Production of BeSang's 3D IC can be more efficient in terms of manufacturing complexity compared to conventional ICs because the memory cells are vertically stacked on top of the logic, which eliminates process incompatibility between the memory core and logic devices. Simultaneously, the amount of time and process steps it takes to process a memory cell in a single chip is roughly the same, resulting in more die per wafer in the same amount of processing time. More specifically, BeSang's 3D IC removes extra mask steps for memory cells from the 2D substrate and uses these extra masks for the implementation of memory cells on top of the logic. Therefore, we can still maintain the same number of total mask steps. So, for example, if the conventional DRAM uses 40 masks per chip, 30 for the periphery logic, and 10 extra masks for the memory core, then 10 extra masks can be removed from the logic wafer processing and be used for the stacked memory cells on top of the logic wafer. A second common misconception regarding 3D layer formation and vertically stacking mask layers is the potential negative effect to yield. The opposite is actually true. Small die size from BeSang's 3D IC will eventually boost yield. As you know, yield increases exponentially as the die size shrinks. Therefore, we expect that overall yield will be maintained or could be even better. Another consideration relating to manufacturing costs is the additional material costs for 3D layer formation. Yes, it is true that there are additional costs for 3D layers, and although we cannot avoid these material costs associated with 3D layer formation, BeSang has come up with low-cost solutions for this problem. The resulting cost is only slightly higher than that of prime wafers. Let's keep in mind that it is crucial to form defect-free and damage-free 3D layers. Let's remember that even though 3D layer formation looks similar to conventional SOI technology, it is in fact far different. Conventional SOI technology for wafer bonding and detaching cannot be used for 3D layer formation because there's no way to cure enormous damages from ion implantation bombardment on the transferred layer at low temperatures. And the wafer bonding method for conventional SOI technology is not at all suitable for 3D layer formation. Okay, so here's the breakdown. Manufacturing costs for BeSang's 3D IC are slightly higher than conventional 2D ICs because of the material costs associated with 3D layer formation. However, there isn't much of a difference in process steps between BeSang's 3D IC and conventional 2D IC. Meanwhile, die per wafer drastically increases, and therefore we can expect high throughput from BeSang's 3D IC. Would it be difficult to develop products using BeSang's 3D IC? Don't worry, you can do it and we can help. For more information about BeSang's 3D IC or how to contact us, log on to www.besang.com. Thanks for tuning in and have a good day.